here we're going to begin learning about trigonometry. So trigonometry has a ton of applications and it's a really broad topic. Its name is very specific. It's actually literally translated to the measurements of triangles. So that's really just sides and angles of triangles, but it's way broader than that and has a ton of applications that you're going to learn about later. Trigonometric functions relate specifically to similar right triangles. So let's consider these two right triangles. We have right angles at B and E, and we're told that C is congruent to F. So by angle, we know that these are similar right triangles. Since they're similar, we can set up these ratios. We know that AB over AC is the same as DE over DF. BC over AC is the same as EF over DF. And AB over BC is the same as DE over EF. And that might not seem that significant, but that means anytime we have this fixed angle, we know the comparison between any two of these sides. So just by knowing one angle and setting up a perpendicular line, we can calculate the comparison between these two sides. And that might not immediately seem powerful, but it's extremely useful. There's a ton of applications that we're going to learn about. I'm just going to talk about it really briefly here. Something called the unit circle. It's a circle that's set up on a coordinate plane with its center at the origin. And we can set up a right triangle anywhere inside of there. And knowing either the side lengths or the angle can tell us something about the opposite. So this is just that written as an if-then statement. If two right triangles have congruent angles, then the ratio between their sides are equal. These trig functions are going to be really helpful to calculate exact values of those ratios based on the angle. There's one more application. I know I'm just going to kind of broadly talk about it, but there's another thing that I want to point out now. It's called a wave function. This is roughly the function for sine. When we graph that on an x and y coordinate plane, and we compare the angle to the ratio of the sides, this is the graph that we get, which is pretty unique compared to the graphs that you've seen before. You've definitely seen a parabola, you've seen linear functions, but you haven't seen something that oscillates back and forth, and this is really helpful because a lot of things in nature behave that way. They go back and forth between two states. So, for right now, we're just going to get into how we compare, or how two sides will relate to a given angle. So, the side of a right triangle that's opposite the right angle, this is our right angle, opposite that side, that is called the hypotenuse. The leg of the right triangle across from the marked angle. So I'm going to have to mark an angle here. Let's say I mark angle C. The one that's across from that is called the opposite side. The leg of the right triangle next to the marked angle, this one, the one that's next to that marked angle, and not the hypotenuse, that is called the adjacent side. So in this case, I marked C, so this would be my adjacent side, this would be my opposite side, and this would be my hypotenuse. It's going to be important that you could use those words flexibly because that is how we talk about these trig functions. So let's just label the hypotenuse, opposite side, and adjacent side for the marked angle. So if this is my marked angle, the hypotenuse is never going to change. That's always across from the right angle. The one that's across from the marked angle is called my opposite side. The one that's next to it is called my adjacent side. Again, across from the right angle, that's called the hypotenuse. Across from the marked angle, that is called the opposite side. And then next to the marked angle, but not the hypotenuse, that's called the adjacent side. The reason those words are important is because that is how we set up each of these three trig functions: sine, cosine, and tangent. A lot of the times, we're not going to use normal variables to represent an angle, we use this Greek letter called theta. So we mark this angle as angle theta. It's the same thing as any variable. We just don't know what that is. It's just traditionally what we use to talk about an angle. So the way we define this sine function, these are three probably new words to you. These definitions come from the ratios that we created on the front. Actually, these ratios that we talked about, this is the sine ratio, this is the cosine ratio, and this is the tangent ratio. So you can see I'm abbreviating those words. S-I-N, that's sine, slightly abbreviated. C-O-S-I-N-E is cosine, but I abbreviate that as just C-O-S. And then tangent, T-A-N, is the abbreviation. So sine of theta is the opposite side over the hypotenuse. Cosine of theta is the adjacent side over the hypotenuse. And then tangent of theta is the opposite side over the adjacent side. So this is going to be completely foreign to you at first, but really you want to think about this as just a calculator. It just figures out what is the ratio between these two sides given some angle. In this triangle, when I talk about sine of A or sine of theta, that means I'm talking about the opposite side over the hypotenuse. So that would be the opposite side. This B got cut off, but that's a B up there. The opposite side would be BC. The hypotenuse would be AB. When I try to calculate cosine of theta or cosine of A, that's talking about the adjacent side, AC, divided by the hypotenuse, AB. And then tangent, that relates the opposite side to the adjacent side. So tangent of this angle, opposite side, that's BC. The adjacent side, that's AC. All right. So we're trying to complete this table. We're writing the sine function here, cosine here, tangent here, using angle P and angle Q. So really, these functions are just calculators. They just calculate an exact value for a ratio with an angle. So sine of P, remember that's opposite over hypotenuse, so sine would be the opposite over the hypotenuse. That would be 4 over 5. Cosine is the adjacent side over the hypotenuse. That one's 3 over 5. And then tangent is the opposite side over the adjacent side, so that's 4 over 3. So that's using this as my angle of reference. That's angle P. Now I'm going to switch it to angle Q, and you'll see that it doesn't really change a whole lot. Using angle Q as my marked angle, the opposite side now would be 3. The hypotenuse would be 5. The adjacent side now is 4. The hypotenuse is still 5. And the opposite and the adjacent switch. Now my opposite side is 3, and my adjacent side is 4. So 3 over 4 is that fraction. So you can see when we talk about opposite angles here, or whatever, adjacent angles there, if we talk about the other angles, aside from the right angle, it's really just changing which one we reference as the opposite side and the adjacent side. Alright, so I actually did not complete the following table for the diagram, similar to previous problems that we just completed. In the diagram, P represents the measure of angle P, and Q represents the measure of angle Q. Use the patterns you notice from exercises 1 to complete the table for Ashlyn. So this is really just getting you to see how these are going to flip-flop. If I talked about the opposite side here for sine, if I talked about the side that's across from this one, but now I change my angle to this one, now it becomes the adjacent side. So these are just going to flip-flop. So sine of Q is the same thing as cosine of P. And cosine of Q is the same thing as sine of P. tangent relates the opposite over the adjacent. And if we're referencing the other angle, that relationship is going to flip. So tangent of Q equals 6/11. All right. Hopefully this at least gets you familiar with these few words that we're going to learn about: sine, cosine, and tangent, and how they relate to a right triangle.